Hello everyone and welcome to lecture today. Today we'll be talking about the simplest type of ODE system that we could obtain, which is a linear system of constant coefficients. We went over in the last class the variation of constants formula in general for first order systems, but today I really want to kind of dive deep into how to obtain the fundamental solution set to a linear system of constant coefficient ODEs. This will, in a very real way, end up giving us some ways forward towards approaching non-constant coefficient ODEs, and also how to classify critical points in general for nonlinear systems as well. So a deep understanding of linear systems of constant coefficient ODEs is vital to really understanding stability of critical points for many nonlinear systems. So what we mean here by first order system of constant coefficient IVP or ODEs is a system where xi prime, xi itself is a vector valued function of n dependent variables, all dependent on t, and xi prime is equal to a times xi, where a is a constant n by n matrix. And we will also have an initial condition, xi of t naught is equal to xi naught. Let's say this is for t in some interval from a to b, which we'll call I a little bit later on. So what we will see is that solutions of this type of system of first order ODEs are very, very, very closely linked and dependent on the eigenvalues and eigenvectors of the matrix A. So this is a little bit of a review from linear algebra. So that A, elements of which are Aij, for I and j from 1 to n. So we let A be a constant n by n matrix. The eigenvalues of A are any real or complex numbers lambda for which the matrix equation A minus lambda times I times U is equal to 0 vector So this algebraic system of equations has at least one non-trivial solution, U. And in general, we will have multiple eigenvalues, and for a given eigenvalue lambda, we call the corresponding solution U the eigenvector associated with lambda. And you could ask, why are the eigenvectors and eigenvalues of A, which you hopefully have a decent amount of practice from your linear algebra class computing, you might ask why these are important to solving this constant coefficient linear system. And what I'll ask you to do is, consider an eigenvalue lambda along with the corresponding eigenvector U, which we call the eigenpair, or an eigenpair of A. So assume lambda is the an eigenvalue and U is an eigenvector associated with A itself, the constant matrix A. And then consider the following combination. Consider the vector function y of t that's defined as e to the lambda times t times the eigenvector u. If you take the derivative of y of t, u is constant, lambda is constant, so this just becomes lambda times e to the lambda t of u. This holds whether the eigenvalue is real or complex. You can show this. And this is the same thing as lambda times the matrix I, the identity matrix, times u, e to the lambda t, which from the definition of the eigenvalue-eigenvector relationship, lambda times I times u, is the same thing as A times u times e to the it, or e to the lambda t, which is equal to A times y, because y is the product of u and e to the lambda t, which means that for an eigenpair of the matrix A, y of t satisfies this differential equation right here. So this clearly shows, why knowing all of the different eigenvalues and eigenvectors of a given matrix A is fundamental to going through and forming the fundamental solution set of linearly independent solutions to a given system of differential equations. And we will start with a study of what happens when we have n linearly independent eigenvectors, and subsequently prove that whenever we have distinct eigenvalues, we will have distinct linearly independent eigenvectors. At the very end, we will go over what happens when this is not the case, which is a distinct possibility. But let's start with discussing distinct eigenvectors, or eigenvalues. We'll see that really all we need is to have n distinct eigenvalues. Suppose that the matrix A has n linearly independent eigenvectors u1 to un. And let lambda I be the eigenvalue associated with or is corresponding with is probably a better eigenvector ui. The fundamental solution set is the set of functions e to the lambda 1 times u1 e to the lambda 2 times t. Oh, it's important. Times t up here times u2 all the way up to e to the lambda n times t un. And so the fundamental solution matrix is the matrix formed by taking each one of these fundamental solutions as a column of the matrix. For the homogeneous system, psi prime is equal to a xi. And all we need to show here to prove this is that the Wronskian is non-zero. And the Wronskian, so we'll call each one of these fundamental solutions xi1, xi2, xi, or actually instead of xi, let's use phi, lowercase phi, like we did in the last lecture. This is phi1, phi2, all the way up to phi n. So the Wronskian of this fundamental solutions matrix as a function of t will be the determinant of this matrix formed by phi1 to phi n, which is the determinant of this matrix. And one of the major properties of determinants from linear algebra is that if you have a multiplicative constant in one of the columns of the matrix you're taking the determinant of, that will come out of the determinant as a multiplicative constant on the entire determinant. So we can do this for each one of the columns. This will be e to the lambda 1t times e to the lambda 2t all the way up to e to the lambda nt times the determinant of u1, u2 to un. And because the UNs are all linearly independent, this determinant is non-zero. And you can rewrite this a little bit simpler. This multiplication of exponentials is the same thing as e to the sum of all the eigenvalues times t times this determinant. And this exponential will never be zero, non-zero, for any value that we put in this expression. And as well, this determinant is non-zero because of the fact that u1 and u2 and all the eigenvectors are linearly independent. So the Wronskian is not, this Wronskian of this fundamental solution set is never zero. And this allows us to go through and compute the, using this fundamental solutions matrix for our system of first order differential equations with constant coefficients. Now things will get a little bit more tricky when we don't have n linearly independent eigenvectors, but we have the following theorem that will guarantee that we will always have linearly independent eigenvectors if we have distinct eigenvalues for the matrix A. So if lambda 1 to lambda n are distinct, which means different numbers, possibly real or complex, eigenvalues, for the matrix A, or of the matrix A, and ui is the eigenvector corresponding to lambda I, then the set of vectors u1 to un is linearly independent. And to prove this theorem, I'm just going to prove the general case when m equals 2. The specific case when n equals 2. But you can hopefully very clearly see that this can be easily extended to the case when m is any higher integer. So we're going to do a proof by contradiction for n equals 2. Suppose u1 and u2 are linearly dependent, where lambda 1 and lambda 2 are distinct eigenvalues So if u1 and u2 are linearly dependent, that means that u2 can be written as some constant times u1. In which case, we can multiply both sides of this equation by the matrix A, and apply the eigenvector relationships for the eigenvector eigenvalues, or the eigenpairs, lambda 1 u1, lambda 2 u2, to get lambda 1 times u2, or lambda 2 times u2. And c times lambda 1 u1. We can also multiply both sides of this expression by lambda 1 to get lambda 1 u2 is equal to c lambda 1 times u1. So I'll call this equation 1 and this equation 2. And if I subtract equation 2 from equation 1, I get a cancellation. Specifically, I get that the right-hand sides of both equations cancel out, and I'm left with lambda 1 minus lambda 2 times u2 is equal to the 0 vector. And since u2 is an eigenvector, u2 is not zero vector, which implies that lambda 1 is equal to lambda 2, which is a contradiction. So we're contradicting our assumption that lambda 1 and lambda 2 are both distinct eigenvalues. So therefore, we've proven the case, our theorem for the case n equals 2, for n greater than 2, the result follows from induction, mathematical induction. Which is a proof technique typically gone over in a discrete mathematics course. But so, armed with this theorem now, we have that if we have distinct eigenvalues, for a constant coefficient linear first order linear system, we have the direct form for the fundamental solutions matrix, or the fundamental solution set. This is a corollary of the theorem, previous theorem, that if A has n distinct eigenvalues, lambda 1 to lambda n, and ui is the eigenvector correlated, associated with, say, corresponding to in the fundamental solution matrix is the matrix that we listed before. With phi I being equal to e to the lambda I times t times the eigenvector ui. And this also gives us a set of n linearly independent solutions. So let's go through and look at a couple of examples. This first example will indicate what happens when we have distinct real eigenvalues. So this will be the differential equation. Xi prime is equal to 0, 1, negative 2, negative 3 times I. The first step is to write down the characteristic polynomial. This will be P of lambda. Matrix A here is this matrix. which is the determinant of the matrix A minus lambda times I, which will end up being negative lambda times negative 3 minus lambda minus negative 2 times 1, which will end up being lambda squared plus 3 times lambda plus 2, which factors to lambda plus 1 times lambda minus 2. And if it doesn't factor nicely, we have to go through and use the quadratic formula here, but it does in fact factor nicely. So then step number 2 is to determine the eigenvalues. These are when p of lambda is equal to 0. Oh, there should be a plus right here. So the eigenvalues correspond to lambda 1 equals negative 2, and lambda 2 equals negative 1, because those are the two roots of this polynomial equation. Step 3 then will be to construct the eigenvectors. And the eigenvectors solve of an eigenvector lambda 1. So we'll say this is AU is equal to lambda 1 times u. And we'll have an eigenvector v for lambda 2. So we have to solve the equation AV is equal to lambda 2 times v. This is a matrix A, which is 0, 1, negative 2, 3. Is equal to negative 2 times u1, u2. And the matrix 0, 1, negative 2, 3 times v is equal to negative 1 times v1, v2. And so going through and solving for the eigenvector u1, u2, you solve this system for u1, u2, you solve this system for u1, u2, you see that any eigenvector, when we solve this system of, so any eigenvector of this matrix A corresponding to negative 2 is going to be of the form of a constant times the vector 1, negative 2, and any eigenvector V is going to be of the form of a constant times the vector 1, negative 1. So we're free to choose which one of these eigenvectors, any value of s here and any value of s here, but the easiest choice is typically s equals 1. And so this means that our fundamental solution set is phi1 of t is equal to e to the lambda 1 times t times the vector u, which is equal to e to the negative 2t times the 1, negative 2, and phi2 of t will be e to the lambda 2 of t, or e to the lambda 2 times t times v, which is e to the negative t times the vector 1, negative 1. Which means our general solution for this example will be c1 e to the negative 2 times t times the vector 1, negative 2 plus c2 times e to the negative t 1, negative 1. Which is the general solution to the homogeneous problem. Now, to specify an initial condition, we can go through and satisfy this by plugging in the initial condition, which is xi of t naught is equal to xi naught, which becomes equivalent to c1 e to the negative 2t naught plus c2 e to the negative t naught. We have negative 2 times c1 times e to the negative 2 t naught plus negative 1, so minus e to the negative t naught times c2 or the fundamental matrix evaluated at t naught, e to the negative 2 t naught, e to the negative t naught, negative 2 e to the negative 2 t naught, negative e to the negative t naught times the vector of unknown coefficients c1, c2, which is phi of t naught times the unknown coefficient vector c. To solve for the coefficients, we would take the inverse of this matrix and multiply it by the initial condition vector xi naught, or phi naught. Which is exactly the initial coefficient matrix, the coefficient matrix c1, c2. The exact expression appears in the variation of constants formula that we talked about before. So this is very cool. This is giving us a definitive way of going through and solving linear constant coefficient systems. And the next example I want to go over is what happens when you have complex eigenvalues. But before I do that, we're going to need a theorem.